They're still married.
I say, what are you doing assuming that?
Yeah.
Like I already stepped forward assuming that he is. I'm just thinking.
There's a comedian I heard not that long ago. It's talking about marriage. This is actually very much a Concordia thing because it seems like students at Concordia get married when they're like 19. Just constantly. They're just always getting married. What is it? Something like 1 out of 4 marriages don't work out or something like that, or have a lot of problems. And so this comedian tells the story. His name's Bill Burr, so he has a lot of a lot of profanity and stuff. So I'll strip that part out. But he says, so why do people keep doing this? They keep getting married. They keep getting married. Now, first of all, I am married. I've been married for almost 20 years. So now I'm just locked in. But he's like, it's like, what if we changed the story? What if we said, okay, instead of it being marriage, what if you were getting ready to jump out of an airplane? Okay, and they say that 1 out of 4 chutes actually open. Okay. So here's 4 parachutes. You got a 1 in 4 chance that this thing's going to open on your way down. Would you jump out of that plane? What's up?
Wait. Take all 4.
Take it. I might need all 4 to fit. Yeah, so it's kind of a funny thing. So yeah, I would. I'd encourage marriage, but I'd encourage you to wait until you know you have the right person. It's always funny if Concordia folks is like, oh yeah, I knew him. I've known him for 3 months, and he's my soulmate. You got to see that person like pissed off. You got to see all the different emotions. Yeah. So, I don't know. All right, so let's pick up where we left off last time. Oh, we got the skull thing there. How do you segue into that? Is that the...
Yep.
All right, so last time we talked about just kind of flipping back through here, reminding us how do human beings solve problems. We use memory, asking questions, and repetition. All right, so then we talked about what's a programming language. Do we have the mapping slide in here somewhere? I want to get that in. So we talk about what's a programming language. A language for giving computers instructions, acts as a middleman between a human and a computer. Now, I'm going to add a slide here. I'm actually going to steal this slide. And then I like to call this guy the mapping. 100% of programming languages provide facilities for these 3 things. The job of a programming language is to take the way that we already solve problems and give us tools for solving problems in the same way when we talk to a computer. All right, because we're not very flexible human beings. We might think that we kind of roll with the punches and stuff like that, but we're not really willing to go much out of our comfort zone to start solving problems. So memory, typically languages introduce a tool called variables. Asking questions, languages introduce a tool called conditionals. More often than not, these are called if statements, and we'll talk about why it almost always is something called an if statement. Repetition, languages introduced through loops, functions, procedures, subroutines, methods, blah, blah, blah. Basically, all these things after loops are synonyms for each other. Just over the history of languages, they've kind of taken on some different names. They all mean the same crap. All right, we'll talk about those. All right, so 100% of programming languages have facilities for these 3 things because they're trying to give us tools that allow us to solve problems the way we already solve them. Make sense? All right, so last time we talked about the CPU. We did the magic trick stuff to have everybody like raise their hand and do like thumb, or I just did it. Like nobody's impressed if I can do that. Nobody's impressed if I can do that. But you do enough of those things in a row and you can pick up a can of soda, things like that. Okay, so when we think about a CPU, we want to think about it like a collection of magic tricks. It has all these little tiny things it knows how to do. And any individual thing might not necessarily be all that impressive in and of itself. But when you put enough of those guys together, you string them together, you actually accomplish something real. Make sense? All right, now did we look at Hello World Linux last time?
Yes.
Okay, so kind of we saw like boring, hello world comes out, right? Just kind of the way we had to kind of set up the trick. So we talked about where's our two kinds of languages, compiled versus interpreted? I'm going to shove this before this. So we talked about there's two kinds of programming languages, interpreted versus compiled. Okay, so did we talk about what a compiler is? Let's throw this guy right after that. So what's a compiler? It translates a high-level language to a low-level language. So somewhere in here, we have to have three kinds of programming languages. So we have our three kinds of programming languages: machine language, low-level, high-level. So we decided computers speak zeros and ones, digital logic, on and off. Not our cup of tea. Two-button keyboard's not going to work for us. Low-level languages, which we looked at last time with the Hello World and Linux assembly. If a human being had to write that, they could, but it's not really a convenient tool for us. But if we had to drop down to that level, we could. I know I threw an extra slide in here at the end to say, when will we still do that? High-level languages, that's our sweet spot. So that's when we write relatively few lines of code, and we rely on a tool to translate that into a whole bunch of instructions for the CPU, which then get directly mapped to zeros and ones. Okay? Because we don't want to do that work. We want somebody else to do that work for us. Then we talked that there's two different kinds of programming languages, even though we already said there's three different kinds of programming languages here. So this is kind of looking at it through different lenses. All right, two different kinds of programming languages. We have interpreted and we have compiled. Compiled languages use a tool called a compiler, which convert from a high-level language that we might use into a low-level language that's going to be right there on the same playing field with a CPU. Where an interpreted language does that on the fly. So a compiled language ends up, can we say this ahead of time? Let's throw it here. So we're going to say compiled languages are relatively fast. Happens prior to runtime. So before we ever run the program, we are compiling that program, so it's already a set of low-level language instructions for the CPU to execute. Make sense? An interpreted language, this guy is relatively slow. This happens at runtime. So we're kind of doing it on the fly, so we would expect there to be some sort of little delay, right? If you are listening to some speech that's being given in a language you understand, and then somebody else is kind of in real time interpreting it into another language, there's a little tiny delay there. Even, it might be pretty fast, but there's a little delay. So interpreted languages are considered to be relatively slow. Compiled languages are relatively fast. Now, I say relatively because our computers are really, really, really fast today. So probably for 99% of any problem you're going to solve, it doesn't matter which of those two types of languages you use. To the end user, the experience is going to be instantaneous runtime. Make sense? Every now and then you might solve a problem that is a pretty complex, really is going to push your computer to some sort of limit. Those are the kinds of problems that you'd want to do with a compiled language. For instance, video games. Okay, we expect those to be fast. We don't want any sort of individual parts of that to have a slowdown, so we're probably going to use compiled languages for those. But just about any other kind of application could be written using an interpreted language. Now we might say, well, why not just do everything in a compiled language? Is it ever wrong to be fast? No, it's never going to be a disadvantage for the thing to be fast, right? Do you think maybe a compiled language is a little bit more complex to create than an interpreted language?
Probably.
Yeah. So compilers are actually very, very complex tools. Because keep in mind, what's the job of a compiler? So we kind of wrote here at top level here. It translates a high-level language into a low-level language. Now, we looked at Hello World in Linux last time, and we, what was it, 15 lines of code or something like that, whatever it was. Let's assume that that is an efficient way of writing Hello World in a low-level language. Could we have thrown a whole bunch of other lines of code in there that maybe weren't even relevant, but it would still go into that program? Sure, it just wasn't necessarily part of the solution, but we certainly could have put it in there. Or maybe we could have moved things, instead of moving something directly from point A to point B, we moved it from point A to point C and then from point C to point B. Maybe we just thought that was going to be better, even though that's more steps. we are at the mercy of the quality of our compilers. How well does our compiler convert our high-level language into efficient low-level language code? Right? Now, over the years, compilers have gotten pretty good. They're producing pretty efficient code. Now, last class, is this the one? So we kind of showed a picture here where the human being, they write in their programming languages. This is usually going to be a high-level programming language, and we'll talk some examples of those in a few minutes. Depending on which language they're using, that either flies through a compiler or an interpreter. We're going to say in the big scheme of things that doesn't necessarily matter, okay? But for certain applications like we just mentioned, it might. At the end of the day, that's going to turn into a low-level language, like assembly, which is then going to get converted into zeros and ones, which is then going to get processed by the CPU. Make sense? CPU is always eating zeros and ones. Human beings are always programming high level. Almost always. 99+% of the time. All right, that makes sense? So the real magic sauce here is that stuff in the middle, the conversion tools. And we are at the mercy of how good those guys are. How well do they take what we said in a high-level language, which has a one-to-many relationship with the CPU, high-level language, one-to-many relationship with the CPU. So we write one line of code in a high-level language, and it translates into a whole bunch of crap on the CPU. All right, so if we want to say hello world, we just say print hello world, for example. And it gets turned into all those lines of code we looked at last time. All right? And keep in mind, last time we were actually using a power tool, even with the assembly language. We were using syswrite from the Linux API. So somebody already wrote that for us, so it does all the magic of actually getting pixels to light up on the screen. So we had the easy version of that. All right, if you roll back into the very, very early days when we really didn't have, let's call it powerful operating systems, or we had significantly less powerful operating systems, you might not have had that convenience. You might have been in charge of lighting up each individual pixel. Well, that wouldn't have been a fun program, and that would have been way longer than 15 lines. All right, so we're at the mercy of these tools in the middle and how well they give us a low-level language that's efficient. So I asked the question last time, when do we use assembly today? Well, we might use it for a classroom example like we looked at for Hello World. All right, but every now and then, we might have a occasion to actually use assembly. And probably the best example of this might be in video games. So I mentioned a little bit ago that most video games, anything we would call a real video game, things that you're playing on Xbox or on PC, things with explosions and things that you care about frames per second. Okay, those things. You're probably not really all that concerned about frames per second on something like Angry Birds. All right, but and Angry Birds would be on the high end of the fun gimmicky games, right? So we're talking about legitimate frames per second. We care about performance. We're willing to go spend $1,000 on a graphics card type of video games. All right, those games have to be fast. And why? Because every single minute they're coming out with new improved graphics and a new physics engine and this, that, and the next thing that make you have to run back out and buy new hardware because the $3,000 machine you built last year can no longer play it on low settings, right? And you got to consider the production time for a video game. A video game might take, let's call it 3 or 4 years to make, something like that, for some of these big games, and with a team of 100 people maybe working on it. So 3 years ago, did we know about what kind of computing hardware we'd have today? No. We got to make a guess, right? We're throwing a dart. We're saying, okay, well, we know what we can handle today. So 3 years ago, they knew the hardware that they had that day. But they're designing a game that's coming out in 3 years. They can't design it for the hardware that day because in 3 years, that's going to look like a stupid game. Or unless the game is like really fun, people aren't going to pay any attention to it because it's not going to look good enough to compete with the other games that are out. So they have to make this guess. They say, okay, in 3 years, we think we're going to be doing time travel. So somewhere in there, they're having to make this guess about what the hardware is going to look like in 3 years based on past patterns. So that's why when a brand new game comes out, almost always, the AAA games, the ones that have a lot of money behind them and things like that, almost always you have like 1 or 2 graphics cards that can play that game with all the graphics turned all the way up, right? Most people, even if they had a gaming rig they put together 6 months ago, have to play that on like medium or maybe high graphics or something. They can't go ultra because their frames per second drop to becomes a flip book, okay, or something like that. Now, having said, how many of you are PC gamers in here? Okay, several hands. How many of you have what you consider to be a pretty good PC gaming machine? All right, what kind of graphics card do we have? 1070? All right, that's pretty good. Anybody have something better than a 1070? We got 1080 Ti? Just a 1080? Well, that's barely better than 1070. Anybody beat a 1080? We have any Titan X's or a 1080 Ti? Or 2 1080s? Nothing, just garbage? What about 1060? Yeah, who else had their hand up? What kind of graphics cards do we have for those of you who said that you had good machines? What kind of GPU do you have? You don't pay attention. Okay, then you're not a real PC gamer. Real PC gamers know the serial number on their GPUs. Is he looking it up? Are you looking up what you got? What graphics card do you have? But you raised your hand, right?
It helps when you build. That's when you know.
No, it doesn't. If you're buying a gaming computer, even if you're not building it, because anymore, to be honest, you might be better off buying one. Because you end up with the number of twists and turns you have to go through to put together the right gaming rig. You might end up spending just as much as if you just bought one off the rack with a. But you should still know what the graphics card is. Otherwise, that's the most important part of the gaming computer. It's like when you went and bought that computer, you said, yeah, I want to play video games, like good ones. It's like, okay, yeah, you want this machine. Okay, I'll buy that one. It's like buying a car and not knowing if it has an engine. It's terrible. All right. So GTX 1070 from NVIDIA is considered pretty good. 1080 would be better. 1080 Ti is even better. Blah, 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 blah. All right. So his 1080, how long have you had your 1080? 6 months? Okay. So you probably paid about $500 for it, something like that. Okay. How long have you had your 1070?
5 or 6 months.
Okay. So you probably paid, what, $350, $400 for it? Yeah. So he paid a little bit more than he paid. And he's got a little bit more horsepower than him. Now, why didn't you go with a 1080? Cheapskate? $100, dude. Skip a couple of pizzas.
The price per power is not.
Yeah, why'd you go with the 1080? Why not a 1080 Ti? Because your friend had one? It's peer pressure. Oh, so you bought one off your friend. So you bought a used 1080. Oh, okay. Yeah. So this is you said like 6 months ago?
Yeah.
Oh, because it was hard to get GPUs. Still hard to get GPUs today. Why? Why is it hard to get GPUs today?
Bitcoin mining. Yeah.
Yeah, it's not Bitcoin, but it's crypto mining. Yeah. Unfortunately, video game PC gamers are in competition with all the people who are using their computers to mine cryptocurrencies. Because they use the same tools, right? Now, guess what? I have good news for you. You have the best cryptocurrency mining GPU.
I'm not going to use it for that, but.
Yeah. Well, why not? What are you doing right now with your GPU?
I'll play games.
No, this exact second.
No.
You could be earning crypto. You'd have that card paid for in like probably 3 months. Yeah, we'll talk. Okay. Now, he will mine crypto faster than you will, but your power consumption is lower. But since Concordia's foot in the bill, he's actually better than you are.
Yeah.
But if you're paying your power bill, yours is better. Comparatively how fast you're earning. All right. Regardless of all that. If we just think about the world of video games here, why might somebody buy a more expensive graphics card than another one? Now we got to think about, so when you get the 1080 and you get the 1070, you're kind of chasing this thing called frames per second, right? You know, frames per second is how many individual pictures will show up on my monitor every single second, right? Okay, because the more frames, the better. Okay, what's your game of choice right now? Okay, and what kind of FPS do you get on that? 200 frames per second. Now let me ask you a question. How many frames per second can your eye see?
My monitor only goes to 6 hertz, so it gets a lot. But
I think the limit for him is 16 frames per second.
It's more than 16. Okay, about, I can see all of them. I see all of the frames. It's like Dr. Locklear's Chuck Norris joke. How many push-ups can Chuck Norris do? He can do all of them. You know, people vary a little bit, but let's just call it around 40 frames per second is what a human being can see, right? Okay, so now you have this really nice graphics card, and then you went and bought a crappy 60 hertz monitor. You don't even have a gaming monitor.
that was my old monitor for my Mac.
Junk, dude. You ran out of money on the graphics card. Yeah. All right. So he has a 60 hertz monitor. So fancy schmancy name for how many pictures can it show per second? Hertz. So his monitor can show 60 frames a second. That's what it's capable of displaying. His eyes can see 40. But he spent money on a graphics card that could pump out 200. We got some bottlenecks in the middle, pal. Okay. So we're dumping 200 frames a second down into something that can only take 60 frames a second, which is spilling into something that can only take 40 frames a second. That $400 graphics card's not looking so hot. Did you waste your money? If I convinced you waste your money? What do you think?
Nah, the experience counts.
What, spending the money?
Building a computer.
Oh, building a computer. You know, you could have done the exact same experience because I'm going to show you the move. When you put a graphics card in, you go.
Memories.
It's a lot harder than that. I'll be honest.
Oh, because you have the full board?
Yeah.
Yeah, so you have to kind of wiggle it around through the wires, right? Okay, there we go. Yeah. Now, the whole computer building thing, I'm talking about just the graphics card. You just crack it in there and you're good, right? So you could have bought a $200 graphics card. It would have gone in the same way. Okay. And you've got one of these other guys that doesn't know about GPUs. You could have handed them the $200 graphics card, told them it was an $800 graphics card, asked them to pay you $600, and you made profit.
I didn't think I get to college.
That's right. I paid for college by selling secondhand graphics hardware with the wrong sticker on it. Now, there's got to be something amiss here. Because, now, well, we had a bunch of hands go up in here for who has gaming computers, even though we had like 2.5 people who actually knew what they had, right? But now, so even within this room, you're not the only idiot, right? We're surrounded by idiots, seemingly. Okay, start with this guy. You're skating along. Now, even outside of this room, there's a giant gaming community, right? Now, there are people who buy better graphics cards than you have. There's people who buy better graphics cards than you have. And then there's people who buy more than one of those graphics cards and actually put it into the same machine and link them together. Use SLI or something like that for well, 2 graphics cards must be better than 1, even though 1 is better than my eyes can see. Why? Are all of these people idiots? Now, you said you get 200 frames a second in your game. Do you always get 200 frames a second in your game? What's the lowest you've seen it drop to? 30. Okay. Now, 30. Your eye can see a little bit more than that, but 30 is it's not like super choppy at 30. 30 is like the bare minimum playable if you only have to deal with it for like a couple of seconds, right? So why do people get these expensive graphics cards? It's not for the average case. It's for the worst case. If you get a budget pleaser graphics card that's running your game at 60 frames a second, the best that your monitor can spit out, okay? And then all of a sudden you get into this really busy part of the game with lots of explosions, lots of stuff going on, and that graphics card drops down to 11 frames a second. You'll notice, okay? And when you finally can see the screen again, you'll be dead. Okay? Game's over. Now, if you're chugging along at 200 frames a second on a monitor that can only show 60, and all of a sudden you hit that really busy area, and it drops down to 30, or it drops down to 50, or it drops down to 80, you're okay. Because we're still better than the human eye can see, right? Or for your case, you're better than your monitor can pump out. That's where you want to spend your next dollars, is on your monitor. If you're a real PC gamer, you need at least 120, if not a 240 hertz monitor. It's just, well, the 4K is not the same thing.
Yeah.
We're talking about frames per second versus resolution. You want at least 120 hertz gaming monitor, which will probably be 4K anyways, but you want a faster refresh rate. Otherwise, I mean, you literally aren't getting your 200 frames per second worth because it can only physically show 60. You're like filling up that glass of chocolate milk, and you just have the gallon turned upside down, and the glass is completely full. And at the same time, you got the straw in there, like the 3-year-old just blowing bubbles. kind of like the yeah. Well, I mean that actually already exists today. Have you been to Culver's and you had Culver's root beer? That shouldn't exist. It tastes fine, but it takes you 5 minutes to fill a cup. Like put a little bit in there, you got like an inch of soda, and it's like all fizzing over the top of the. They have an invention for that. You know, you can put your finger in there, and it'll go down really quick. Yeah. They need to have something like that replaces that. Well, there's a trick with spaghetti, actually. So you're learning. It's like, what? How do we go from graphics cards to spaghetti? Okay, you know how you have to like pay attention so that it doesn't boil over? Yeah. You know what the trick for spaghetti is? What? To keep it from boiling over? Well, well, actually, that won't work. If you have the heat too high, stirring it's not going to necessarily help. It'll just kind of like in slow motion let you monitor it boiling over. You take a wooden spoon and you just put it over the top of the like cover make sure it's long enough to go across the radius of the pan, and just leave it there. And as the bubbles come up, the wooden spoon will make them go down. They won't overflow. Life hacks. Right? Then all you have to worry about is making sure you have light enough pasta that when it's boiling, it comes off the bottom. It doesn't just burn to the bottom. That's why they make everything with those little tiny, what are they called? What? No, that's not light enough. You need the stuff that's like macaroni, but even smaller, like the little dots of pasta. It doesn't even have tubes or anything. It's something like that, you know. So it does look similar to that, but it's not. But whatever. All right, back to gaming. Now we've covered the details of spaghetti. Okay, so you buy this extra cool graphics card so that in your worst case, it's a acceptable case, right? Mm-hmm. So fine. Now you seem like less of an idiot. Now like, oh, okay, well, I'm a diehard gamer. You know, my performance is important. So my hardware needs to be able to keep up with all the games I'm playing, right? And even if I'm getting 200 frames per second most of the time, that's insignificant because I'm not processing 200 frames a second. It's in that worst case, okay, when there's explosions and all this stuff happening that I can keep playing, okay, where the guy who's getting 11 frames a second is sitting there looking at a flip book on his screen and can't do anything. All right. Now, having said that, so, you know, that kind of, we're proving the point here that computer games expect performance, right? They need to be fast. Now, every now and then, so they're writing your computer games in probably a language like C++, let's say. And in C++, they're running that through the compiler, and it's going to spit out some assembly code. Now, when we really focus in on those parts of the game that have a lot of those explosions, those things that really need to be fast, because, I mean, the situation is already bad, right? Mm-hmm. It's already going to be stressing all your computer hardware and things like that. But when, you know, the designers are looking at it and says, like, look, we want this scene to look as awesome as possible. We need this to be as fast as possible. And oftentimes we have some limitations with modern computer, well, really any kind of computer language. Computer languages force us to be unambiguous, and computers are also stupid. So they don't necessarily know what we know. We might be writing a portion of this game, let's say, and we might know as humans that certain types of input will never happen. Okay? But when you're writing the software for that, you might have to cover all your bases. The language might force you to ask all the questions so that it can ultimately give you an output. Even though you know you might ask 7 questions, and you know that 4 of them are complete wastes of time. Because you know as a person that those conditions will never be met because of the nature of your game, and you know how people are playing it, you know what the input devices look like and stuff like that, right? But the programming language doesn't know what you know. The programming language was built to be a general purpose programming language for solving all sorts of problems. So you might be forced into doing some extra questioning in order for the thing to compile and spit out some results. Then you know you would have to do, just to follow the rules of the language. So then you might go in and say, okay, well, now it's giving me some assembly language, but I happen to know, even though it did give me a pretty efficient output of what my input was. My high-level language, I wrote it this way. My output, my low-level language is equivalent to that. Let's assume it's efficient. But you know there's some extra crap in there. That make sense? Mm-hmm. So maybe at that point, you would go and you would edit some of that out because you know, I mean, you realize that you are creating some pathways here that if you were ever to get in there, your program's going to crash. So you have confidence that because your user only has 4 buttons on their joystick or something like that, that they're not going to hit button 5 or 6. For example. Okay, so you can kind of take that out. Make sense? It's in situations like that where you decide you might go in and modify the assembly language a little bit. But I mean, that's really, really situational. Okay, because you're probably not going to waste your time doing that for the parts of the game that you're getting 200 frames a second, because those aren't really pushing the hardware. An extra 2 or 3 questions here and there is not going to be a big deal. It's really during that part that everybody complains that their frames drop to nothing. Okay, and then, you know, this guy's over there, oh, I got this 1080 back. I didn't even notice anything on my monitor. It was fine. Okay, in fact, it played the scene for me. It didn't even have to shoot. Now, having said all this, the good news for you gamers is even though I've said the human eye can only see about 40 frames a second, you can perceive the difference between 40 frames per second and 200 frames per second from a smoothness perspective. You're not seeing the frames, but you might notice a little bit more jitter or something like that at 40 frames a second than you would at, well, in your case, 60 frames a second, even though you're pushing, yeah, it's embarrassing, really, actually. I don't even get it. I have a laptop that goes 120 frames a second, and it has a 1070 in it, too. It's just garbage, dude. And I don't even use it. It's not powerful enough. So, yeah, I use it usually to keep my coffee warm. Yeah, so, you know, I mine crypto on there. It keeps it toasty, right? And I just put my coffee mug on top of it, keeps it nice and keeps it warm. Sometimes it's tea, not always coffee. All right, so, you know, that's where assembly might really come back into play for us. We're talking really, really, really rare. Okay, probably less than 5% of all video games would even consider this, and you know, way, way, way less than 5% of any part of that game would care about that. All right, but the punchline here is that for those of you who are spending money on your graphics cards, the better graphics card is better for gaming. Even if your human eye can't perceive the difference, you can perceive the smoothness difference. All right. But if you're a gamer, definitely get a fast enough monitor to keep up. I mean, if your graphics card can only put out 50 frames a second, don't waste your money on a more than a 60 hertz monitor. You know, but the same argument translates when you go into to Best Buy or something. You're buying a TV. You know, your standard HD TV is 60 hertz. You know, but then you can get 120 or 240 hertz ones, and you're like, well, why are they so much more money? They say, well, do you like watching sports? Something like that, and you're thinking they're just selling you crap, right? If you ever watch a football game on a 60 hertz HD TV, if you pay attention, sometimes you'll see some shadowing. When the football's flying through the air, you'll see like 3 footballs. Just little tiny shadows of the football behind it because the frames are moving across there, and those games are moving fast, right? And you'll actually see that little shadowing on a lower hertz monitor. Even though you can only process 40 frames a second, you're perceiving that smoothness, the transition between frames. So 120, you'll be good. 240, probably overkill, but if you play a lot of games, 240 would be pretty solid. Kind of future-proofing. Okay, so we kind of already mentioned this a little bit. 2 types of programming languages. We have domain-specific, we have general purpose. So I kind of mentioned a few minutes ago that are most of our high-level languages that we're writing video games out of, for example, which, it's not a video game class necessarily, but just it's a good example for computer science. But, they're general-purpose languages. These are languages built for solving a huge, huge classification of problems on computers. All right, as opposed to domain-specific languages. And these are languages that are built to solve very specific problems. Maybe you might have a programming language for running a dishwasher, where a dishwasher has like 4 or 5 different cycles, something like that. Do you think that language is probably far smaller than one of these general-purpose languages for, creating operating systems or Microsoft Word or something like that? Sure. But these are both still programming languages as long as they have facilities for memory, asking questions, and repetition. Make sense? All right. There's 3 kinds of programming languages. We got functional languages, we got procedural languages, and we have object-oriented languages. Now, I'm not really going to talk much about functional languages here because it doesn't really pertain to us most of the time. When you take the, how many of you are CS traditional majors as opposed to IT? Okay, so when you take 470 with me in a couple of years, we'll be using a functional language in there called Scheme, and we will create our own programming language. Functional languages, if you've ever used a graphing calculator, like one of the Texas Instruments graphing calculators, that has a functional programming language in it where everything is done in terms of functions. You can take the sine of the cosine of the tangent of whatever, and just kind of list those guys all together in just one big kind of hodgepodge. That's what a functional language looks like. Forget about it for us. I'm not going to ask you any questions about it. It's not pertinent to traditional programming. We do care about procedural versus object-oriented. So procedural languages tend to be monolithic in nature, where you have a lot of code that is executed linearly, and all the details are seen all of the time. Okay. Might be kind of a little bit of an exaggeration, but it'll help us tell the difference between these. All right, and now a good way of kind of describing procedural versus object-oriented is using an example. So let's say that over here on the table, I say I have a telephone. Okay, there's a telephone. Now, how many of you in here think you can identify a telephone when you see one? Most of you, right? But just most. Not every hand went up, by the way. Typically, you have poor voter turnout in classes. It's garbage. Now, but this is going to be a very special telephone. When you walk in, there's actually going to be a giant pile of wires on this table. And at first glance, you wouldn't look at that and say that's a phone, right? So that's a mess of wires. And you come over, you investigate it a little bit, you find some buttons, you find a little headset, you listen, you hear a dial tone, as if those exist anymore. How many of you have heard a dial tone before? How many of you have heard a dial tone in the last year? Really? Where did you hear one in the last year? Some payphone in a foreign country?
No, I was somewhere around Chicago, and I found an old payphone.
Oh, so it's still a payphone. Picked up a dial tone. What the heck is that? It's an alien signal. What was yours?
Grandma's house.
Grandma still has a landline. Yeah.
One last year.
Yeah, but rare, right? You don't have the dial tone in your cell phones and things like that. Yeah.
My work has it.
Your work they have fax machines, right?
Yeah.
Okay, but in any case, you're messing around with the wires. You hear the dial tone, blah blah blah. Finally, you're convinced that that pile of wires over there is in fact a telephone, right? You can find all the individual buttons. You could probably make a phone call, but it didn't look like a telephone. When you walked in, that didn't look like a telephone. You had to be convinced of it. That's a procedural version of a telephone, right? All the wires. Now we know. We take a phone like this. We know there's a whole bunch of really complex stuff inside of this, right? And we might be impressed about it for a second, except for those of you who don't know what kind of graphics cards you have who claim to be gamers. But the point is that we trust that some smart people built this thing and made it work inside. And we don't care. We don't. At that point, we're not cracking it over and kind of tweaking wires and stuff, right? For the most part. What are we doing? We're only using the public interfaces of the phone. We need the touchpad to dial numbers. We require the little mic, the speaker up here, and then the microphone down here so you can make your call. We're only interfacing with those public parts that are actually required for us to make the phone work, for us to solve problems with the phone. We rely on all those wires working, being there. But once they're working, and once they're all set up, they're hidden from us, right? Because we don't need to see them anymore. That's the object-oriented telephone. Make sense? Object-oriented telephone looks like a telephone. So it's a container that holds all of the details that we would have in the procedural version, but they are hidden from us, and only the public interfaces are exposed. Now we look back at this wall in the back of the room. Do we think there's probably some power cords and stuff like that inside that wall? Okay, that we rely on. If we put something into one of these plugs back here, we want it to give us some electricity. Right? Somebody might be charging a laptop or something back there. We're using the public interface from that power cable, but those cables are hidden from us because when the place was built, they made sure they worked, then they put plaster up or they put drywall up, whatever. Now, if we really needed to get to those wires with a hammer and some willpower, we could do it, right? Okay, but a majority of the time it's hidden from us. So object-oriented programming, all it is an organizational model. They're taking an older language and just giving you one piece of Tupperware. It allows you to wrap the stuff and poke little holes in it and only pop out the things that you actually need to use when you solve problems with it. Make sense? All right. Remember, you have your first Bible homework due by midnight tonight. I will see everybody on Monday.